so welcome back. Today, we learned a little bit about molality, total molality, and mole fraction. Now, where we're going with all this is to be able to predict how dissolving something into water is going to affect its boiling point, its freezing point or melting point, and also its vapor pressure. Now, before we get into those equations, which actually aren't too hard, by the way, we need to be very confident and proficient calculating molality, total molality, and mole fraction. All right. So what we spent time on in class today was just that, kind of going over the ins and outs, how to make that calculation. So this tutorial will walk us through an example. Right. So in this particular case, we have 112.3 grams of calcium nitrate, and that's dissolved into 250.0 grams of water. That's a very typical way to start a prompt for these types of questions. And so what we're going to do, we're going to take those numbers right there. We're going to figure out its molality. We're also going to figure out its total molality and also the mole fraction, just one step at a time. All right. So we are going to start with a dissociation reaction, because we are dissolving this calcium nitrate into water, which does change the properties of that calcium nitrate. So I'm going to write that in red just to mix things up a little. All right. So calcium nitrate. Remember, look on your periodic table. You see calcium is +2, nitrate is -1. You get that from your polyatomic ion sheet. So the formula of calcium nitrate is CaNO3 2. All right. Now, when I dissolve that into water, I am going to separate that compound, that ionic compound, into its individual ions. We know this is ionic because calcium, metals always make our ionic compounds, right? So as I dissolve this, I'm going to get a calcium ion with a 2+ charge and 2 nitrate ions, right? Now, notice this being a polyatomic ion, I don't mess with that subscript attached to the polyatomic ion, but I do focus on that 2 outside the parentheses. So just a quick reminder of that. All right? So that is my dissociation of calcium nitrate into water. It separates into its individual ions. I'm going to leave that up there for the rest of what we're going to do, and this will be important particularly for our total molality here in just a minute. All right. So I have specific amounts of calcium nitrate and water, and I want to find my molality. So molality, my little m, is going to be equal to my moles of solute over kilograms solvent. All right, and solvent is almost always water. It doesn't have to be necessarily, but for our calculations, we're just going to use water for almost all of our molality calculations, right? So solute, whatever gets dissolved in the water, in this case, calcium nitrate would be our solute. So my moles of solute, right, would be equal to my mass of solute divided by its molar mass, right? So just to show that work right here, I've got 112.3 grams of CaNO3 and I've got 164.10 grams per mole. And that gives me a whopping 0.684 moles of calcium nitrate. All right. So my number that goes in for moles of solute would be 0.684 moles. Right. So let's say little m is equal to 0.684 moles over a kilograms of solvent. All right. Now, I mentioned in class today, and I'm going to mention it again. One thing I want us to be good at is not having to think too hard about how to convert from grams to kilograms, right? To do that, I see that, I automatically know, okay, 250 grams is 0.250 kilograms. All right, I know that because to go grams to kilograms, I move the decimal left 3 places. Done, don't have to think about that. Now I can make my final calculation for molality would be 0.684 divided by 0.250. And when I do that number on my calculator, I get 2.74. Okay? So my molality in this case is 2.74 moles of calcium nitrate per kilogram of water. That's what that concentration would come out to. All right? So I have that. I've just calculated my molality. All right? Now, I've made a couple calculations here that might come in handy later. For example, my 0.684 moles of calcium nitrate. So I'm just going to write this off to the side. So I'm going to come back to that number later. All right. Now we can focus on total molality. All right. So as we just mentioned, my molality is 2.74. Right. So I'm going to write that number underneath here. And that's to indicate that I've got a molality of 2.74 moles per kilogram, where that's my solute, right? Now, I wrote out my dissociation reaction because my total molality, right? My MT is going to be a little different than my molality. Because again, what's happening here is I've got 2.74 moles of calcium nitrate particles, like where they're still stuck together before they dissolve, per kilogram of water. Now, once I dissolve that into water, all those individual particles actually separate from each other, right? So those 2.74 moles are going to get distributed out amongst all those different particles, all right? So the way that looks here, I got 2.74 moles here. Now, it's a 1-to-1 ratio for my calcium, right? So this would also be 2.74 moles, right? Now, the trick here is because I have a coefficient of 2 and a 1 here, I need to double again that mole. So because I've got a 1-to-2 ratio, so I'm going to go plus 2 times 2.74. Right? So essentially my total molality in this case is going to be 3 times my original molality before I dissolved it. Alright? So 2.74 plus 2 times 2.74, when I do that calculation, my MT, total molality in this case, is going to be equal to that, which should give me a whopping 8.22. All right? So again, what I did here was I found my original molality, which was 2.74, right? Now, because we separate this the single particles of this into 3 different particles, right? 2 from nitrate, 1 from calcium. I'm essentially tripling my molality by separating those into their individual particles. All right? That gives me a total molality of 8.22. All right? So, now again, the molality and total molality, you have to be able to do this to be able to proceed and to see the effect on boiling point and melting point and so on. All right? So, that's just an example of that. Last thing we'll now figure out is our mole fraction. Our mole fraction, by the way, we'll learn this tomorrow, has to do with how it affects the vapor pressure. All right? So mole fraction, fairly simple thing, and it's also why I kept my moles of calcium nitrate over there. I'm going to come back to that because a mole fraction equation of water in this case, typically we're trying to find out how the vapor pressure of water changes, so we're going to know the mole fraction of water. Water being our solvent, so it's X solvent equals moles of solvent over moles solvent plus moles solute. Right? So me thinking ahead, I already calculated my moles of solute. I didn't want to do that calculation again. That's why I wrote it down right there. So now I just got to figure out how many moles of solvent I have. So how many moles of water do I have in this case? So I find that just like I normally would. So I need to know my moles of solvent. Right? So I have 250 grams of water. Right? And convert that into moles. So the molar mass of water being 18.02 grams per mole. Right? And what that gives me as a result is 13.87 moles. Of water. Now I have the 2 numbers I need to figure out my mole fraction. Alright? So X solvent is going to be equal to my moles of solvent, which is 13.87, over 13.87 plus 0.684, right? And I punch that in my calculator, I go this, divided that plus that, make sure I add those before we divide, right? And I should get a mole fraction of 0.953, and that 0.953 has no units attached to it because it's just a fraction or a factor by which we're going to multiply later. All right, so this accompanies, by the way, your ChemQuest number 40 that I just handed out today. That's the colligative properties. All right, and next installment will be how to take this stuff and then apply it to figure out what's my freezing point going to be at various concentrations, what's my melting point going to be, what's my vapor pressure going to be, which are important predictions to be able to make in chemistry. All right,